Okay. Uh, I use the mic or can you guys hear me? Mic? Yes? Alright, bet. Okay. So, good morning, good afternoon, good evening. Today is, what day is it today? March 18th or something. We're gonna be doing the OChem 2 practice, OChem 2 exam from spring of 2022. This is your guys' second exam. You have the exam on Friday at 7 p.m. Please be ready. Okay, so to begin, Um, we're gonna start with the nomenclature section. So in this question, it's asking us to give an acceptable name for each of the following compounds, and according to IUPAC, right? So, the first one that we see a benzene group. We see a benzene with a ketone attached to it directly, and then a ketone attached. Let me a ketone that is attached 1, 2, 3, 4 carbons away. So, in this one, in this exam especially, it's very important to remember the benzene compounds that Dr. Bean has discussed, such as like anisole. There's the benzoic acid, benzaldehyde, all those. So make sure to remember those. This one, this group is called a acetophenone. So this is going to be our parent chain. So parent acetophenone. Right. And so because that's the parent chain, this chain that's coming off, that second ketone is going to be our substituent. So for our substituent, we're gonna label it as a pentyl group, right? But it has the double bond to the oxygen on carbon 4, and that is called an oxo group. So oxo, right? So our substituent is gonna be called 4-oxo pentyl, right? And so that's going to be our substituent, but that's going to be on the opposite side from this carbon, right? So if we were to count the benzene ring, 1, 2, 3, and 4, it's on carbon 4 of the benzene ring. So we're gonna put 4 there. We can also put para, like the P, but I think it's just easier to put like just the number. You get the full credit for just using the number as well. So now we have our substituent for 4-oxopentyl, and then our parent chain acetophenone. We don't have any stereochemistry in this problem, so we're just gonna put it all together. So 4 dash pentyl goes acetophenone.
Which year?
This is 2022. Right. So are there any? But yeah,
Not used.
you can use orthopara for the naming. I just think it's easier if you just put the numbers, because then if you sometimes you might get confused orthopara meta. It's not required. No. But you can put it for a lot. All right. Um, any other questions? Next one. So this time, we have two benzene groups, and then we have an aldehyde group, right? So in this one, our aldehyde group is going to be part of our parent chain. It's going to be the highest priority group there. So we'll start at the counting at the aldehyde, right? And then we'll get the longest chain that we can from this aldehyde. So if we count this carbon with the oxygen as number 1, we can continue with the longest chain. So 2, 3, 4, 5, right? So it's a 5-carbon chain, so it'd be a pentane, right? So whenever we have an aldehyde, it's gonna change the parent name a little bit. So this pentane is gonna go from a pentane to a pentan, right? Sorry, we're gonna have it to be pentan, pentan, and then to indicate that we have an aldehyde as our parent chain, we're gonna add al at the very end, right? So our parent chain is going to be pentanal. And one thing to note, whenever you have an aldehyde, it's either ever going to be on the first or last carbon. There's not going to be any like how do you say uh like any aldehydes that would be in the middle of the chain, right? For example, if there's an oxygen here, that would be a ketone, right? There's not going to be any aldehydes like that, right? So this aldehyde that we have here is going to be at the end of the chain, and since we're starting to count from it, we don't have to put that it's at one pentanal, right? It's just automatically assumed that the that it's going to be on the first carbon, right? So let's start naming our substituents. So we have a substituent on carbon 2 and carbon 5, right? So they're both the same. They look to be the same groups. One of them is if we cut this from here and this from here, we can see that they're slightly different, right? One of them has CH2, then our benzene group, right? While the other is just a benzene group that is connected, right? So whenever we have a CH2 benzene group, that is going to be a benzyl substituent. So BENZYL. And whenever we have just a benzene group that's coming off with no CH2, that is going to be a phenol, right? So putting it all together, because we don't have any stereochemistry, we can just finish this off. This is going to be a 2-benzyl dash 5-phenyl pentanal, right? Any questions on how I got that answer? Yeah, AL, yes. Any other questions? Make sure that whenever you're putting all of these, they're all going to be in one word, right? Try not to have any excessive spaces in your writing, otherwise they could count off points, right? So, if there are no more questions, I'll go to the number 3. So, for number 3, it's a little bit of an interesting problem, right? We have the alcohol, we have the ketone, and we have the alkene, right? So we have three potential parents, right? So from this, the alcohol is actually a lower priority than this ketone, right? So the ketone is going to be our parent chain. We'll count it as the parent chain as the ketone, right? So we're not going to start numbering from the ketone because it's in the center of the carbon, but remember, whenever we want to number longest chain. That includes both. That includes the parent, right? So if we go from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's also count from backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice how on both of them the ketone is on carbon 5, right? So now let's look at the substituents. So we have the alkene substituent right here, and we have the alcohol substituent, right? So with the green numbering, it's going to be at 1, 7, whereas for the blue numbering, we have them at 3, 8, right? So because the green numbering has a lower numbering, we're going to be using the green numbering as our chain. So we'll start. Um, okay. So to name the parent, we know it's a 9-carbon chain, so nonane, right? And because it has a double bond, it goes from nonane to nonene, right? NONENE. And to indicate that it has a ketone on it, we're gonna drop the E at the very end of nonene, so non-N, and then we're gonna have one, right? So that just tells us that this is a ketone, right? Ketone. And this tells us that this is a alkene. Okay. And so we will have to put like the numbers for it. So there are two ways that we can do the numbering, right? So in this one, whenever we have two of the groups in the parent chain, uh we're actually gonna have to put a number in the center, just because there's no other way to really indicate that there would be that there would be a carbonyl at carbon 5 and the double bond at carbon 1 at the same time. Like for example, if you put 1 comma 5 non-enone, right? That just tells you that we have two double bonds at 1 and 5, and then not a ketone on carbon 1, which it will probably look like this, which is very weird, right? So that's not what we want. So we're gonna have to put 1 dash nonene dash 5 dash own, right? Or we could do non dash 1 dash in dash 5 dash own, right? So both of these are acceptable parent chain names. And then lastly, we're going to be going at our at our substituent, which is the hydroxy group at carbon 7. So 7 dash hydroxy. And now looking at this, we do have stereochemistry because we have wedges and dashes on a chiral carbon, right? So this carbon is chiral, and we have 4 different groups attached to it. So we'll start doing some numbering. So from this, the hydrogen is going to be our smallest group, and our OH is going to be our largest group, right? But now we have the choice between these two carbons. So carbon 8 has 1 carbon connection and 2 hydrogen connections. And carbon 6 also has the same thing, C, comma, H, comma, H. So we'll go to the next one. So carbon 9 is going to have 3 hydrogen connections. And then carbon 5 is going to have 2 oxygen connections and a carbon connection. So the group on the right will be bigger than the group on the left. So we'll put 2 like this and 3 like this. We'll draw our arrow, and this is going to be a counterclockwise arrow, which tells us that it is S, right? And because the largest group is on a wedge and the smallest group is on a dash, there's no need to change it. So this is going to be S as our stereochemistry. And if we put it all together, S dash 7 hydroxy dash non, well, 1 dash non dash 5. And that will be our parent chain name. Are there any questions on how I got that answer? So moving on onto the facts section. So this facts section, going to be quite interesting. So the first one is asking to label the molecules below as aromatic, anti-aromatic, or non-aromatic. So please assume all are planar. So because of this, please assume all are planar. We're gonna have to assume that all of them are sp2 hybridized, right? So even for example, this oxygen, this is sp3. This is an sp3 oxygen, 1, 2, 3, and 4. It's asking us to assume that it's all planar. So let's just assume it's sp2, right? And so we'll go on to that from the next one. Let's look at the first one. So one thing to note, aromatic are gonna follow the rules of 4n plus 2 pi electrons plus 2 pi electrons, right? And then anti-aromatic are gonna have 4n pi electrons. Then non-aromatic are either gonna be sp3 or yeah, they're pretty much just gonna be sp3 non-planar, right? So we'll get into that whenever we talk about it because it does say to assume all are planar, but we will figure it out. So the first one, every double bond that you guys see is gonna count as 2 pi electrons. Okay, so because all of these carbons are sp2, this is sp2. All the carbons that you see on this molecule are sp2. All we have to do is just count up the amount of pi electrons. So in this we have 1, 2, 3, 4, 5, 6. So this is going to be 6 times 2 is 12 because we're going to say 2 electrons, pi electrons per double bond. So 12 follows the 4n rule, right? And because there's no resonance in this molecule, there's no way to make it um, non-aromatic. So we're going to have to call this anti-aromatic, right? Okay, so next one. Whenever we see this, it's very important that we should do some resonance structures. So the first resonance structure I'll do is going to be like this, because this we have this molecule and this molecule as both being sp3 hybridized, right? So we'll draw two resonance structures that show that both of them would be sp2 hybridized. Okay. So whenever this creates a double bond right over here, then this causes the minus charge to go onto this oxygen, right? So what that looks like is going to be like this. Um, Oxygen. There's a minus charge right here. Plus charge. Right, perfect. Okay. So this is going to be our molecule, right? So this this oxygen is going to have a plus charge as well. So this is our molecule. It doesn't look very nice, thing is it has 4 charges, but this is one of our resonance contributors. We look at this way. This oxygen has a lone pair attached to it, including this double bond and this double bond. Right. So in this one we have 6 pi electrons. And let's see the other way. So remember, we can't go this way because this nitrogen would have 5 bonds. That is not energetically favorable. So we're going to go this way and do the same thing. Essentially just make this oxygen have a minus charge again, but from the top. So we have this. Oh, then this is a minus. Okay. So this time, if we count this one, let me see a second. That's a minus charge. I think that's all right. All right. So now that we see all of this, um, we can look at this one, and this oxygen still has a lone pair here. So we have again 6 pi electrons, right? So in both those cases, we follow 4n plus 2. Whereas if we looked at this case, this would be non-aromatic because this oxygen and this carbon are that these molecules are planar or non-planar, right? They're sp3 hybridized, not sp2. But whenever we do some resonance, and we assume that all are planar, then we find that they have 6 pi electrons in the hybrid, right? And so because of that, because these are both aromatic, it's always gonna go for the most stable hybrid, right? So this molecule is gonna be aromatic. So next one. So whenever we have this double bond, what we can do over here is we can cause it to make this into a double bond and then put this minus charge onto this carbon right here. So what that'll look like is right. So if we count this up, we have 1, 2, 3, and 4. So this is going to be 8 pi electrons. This tells us that this is anti-aromatic, right? But if we look at this one, this molecule tells us that this is going to be non-aromatic because this nitrogen and this minus charge are going to be sp3 hybridized, right? So because they're sp3 hybridized, they run the chance of being non-aromatic rather than being anti-aromatic, which is very unstable, right? So because non-aromatic is the more stable of the two, we're going to call this non-aromatic. Okay, and for the last one, we have a boron right here. So boron is one of those elements which is very happy with only 3 pairs, right? Boron has 3 valence electrons. So if it has 3 pair, like 3 bonds to it, it doesn't need another one to be happy, right? So if we look at it this way, now we have all the carbons are sp2 hybridized, right? Or everything in the rings are sp2 hybridized, and this time we have 4 double bonds, which equates to 8 pi electrons. So because of that, it follows the 4n rule. And because there's no resonance here, because boron does not have a lone pair, since it follows the 4n rule, this is going to be anti-aromatic because there is no resonance. So notice, whenever we did have resonance, we used resonance so that we could see if there was a more stable one. So for example, for this one, the original molecule that we see is non-aromatic, but whenever we did resonance, we found that it was aromatic, and so we labeled it as such. Versus this one, it started as non-aromatic, but then whenever we did resonance, we found it was anti-aromatic, so we called it non-aromatic because it was non-aromatic is more stable, right? Any questions on that? Yeah. Mm-hmm. So this carbon right here is already sp2, right? But this carbon would be considered sp3, like just like this. Right, but the it has we're assuming that all of them are planar, right? So even though it's sp3, we're still gonna count it. Then yeah, we wouldn't count that. It would just but most of the time whenever you're gonna be using aromatic or anti-aromatic, they're always gonna say assume all are planar, just so that you can figure out the question, do resonance, find it out. Yeah. Any other questions? All right. Okay. So next question. Rate the following substituted benzene compounds in order of increasing rate in the reaction with CH3Cl and AlCl3. So this is going to be Friedel-Crafts, right? So FC. So whenever we have Friedel-Crafts, this is going to be an EAS reaction. And so we EA right? So these are going to be EDGs that are going to be following right off the benzene, right? So let's look at the first one. In this one, we have 2 methyl groups. These are both EDGs by induction. So they're pretty weak. So it could be. This amine group, however, is an electron withdrawing group, right? So this is going to be not favorable, not good. Or I'll just write bad. And the next one we have in amide. So that's whenever we have the carboxyl group with the amine. So because of this, this is actually going to be an electron donating group. So now whenever we do this, uh, for example, to put into perspective why it's an electron donating group, this electron withdrawing group is going to be wanting to withdraw electrons from the most partially negative atom there, right? So it's going to want to pull from this double bond. Versus this amide group is going to want to pull from the oxygen, right? So it's going to go towards the ring rather than away from the ring. And this one is also going to move towards the ring, right? So those want to pull electrons through versus this electron withdrawing group wants to pull electrons away from the ring. So, this is going to be EGG by resonance. So if we put it all together, we have an electron withdrawing group. This is going to be our slowest rate one. Then we have our electron donating groups, one by induction and one by resonance. And we know that resonance is going to be stronger than induction. So our resonance is going to have our fastest rate, the second fastest rate. Any questions on that? I got to that. Oh, yeah.
I don't know, by induction.
So whenever most of the time donating by induction just means it doesn't have any resonance, right? So this is gonna be like very nonpolar atoms like carbons. This is I think the only thing you're gonna see is carbons being donating by induction, right? Or maybe halides. Yeah. Aldehyde is gonna be donating is not aldehyde actually isn't a donating group, it's a withdrawing group, right? But it's gonna be withdrawing by what's it? Because it has the double bond and the lone pairs is gonna be withdrawing by resonance, not induction. Yeah. Yeah. Mm-hmm.
For the middle one, for the second, three,
Mm-hmm.
two, because, it's in auto groups, and then three, because it's a need, and I know that needs like a stronger domain group than just like our
Mm-hmm.
group. So, based off that one, that that's about the reaction rate.
Yeah.
It's like three, and the is two.
Yeah. Okay. Yeah, perfect. Any other questions? All right. So on the third facts questions, it's asking rate the compounds in order of increasing reactivity in a nucleophilic addition reaction, right? So in nucleophilic addition reactions, so NAS, we have the option between aldehydes and ketones, right? Aldehydes versus ketones. So and for aldehydes, one thing you guys have to know is that aldehydes are much more reactive than ketones, right? So they're more reactive than ketones. So because of that, both of these are aldehydes, so they're both going to be more reactive than this ketone right here, right? So we can already put the ketone as the least reactive, even though it would be plenty reactive. So now, our second part is to look at, you can look at two things, right? For this one, I'll focus on, I'll look at dipole induction, and then we'll look at steric hindrance right after, right? So whenever we have the partially positive, so whenever we have an NAS, we want a partially positive carbon, right? So both of these carbons are partially positive, but one of them is getting electrons donating to them like twice as much as this electron, right? This one is only one methyl group that is being an EDG versus this one is having two methyl groups being an electron donating group. That's going to cause this partially positive carbon to be slightly less than this partially positive carbon, right? It's going to be slightly more versus this one on the left is going to be less. So because of that, because we want a more partially positive carbon, this is going to be our second most reactive, and this is going to be our third most reactive, right? And you can also look at this from a steric hindrance point of view. If you're going to be attacking something, this partially positive carbon, right? You would rather have one methyl there than two methyls there that could block your way, right? So because of that, it's still going to be the same thing, both steric hindrance and by dipole induction, right? And then the ketone is going to be our least reactive compound. Does that make sense to everybody? Questions? All right. So next one. Place the following compounds in order of increasing frequency of the CO stretch in the IR spectra, right? So there's two things that we have to look at in this. So we have double bonds and we have conjugated double bonds, right? So conjugated double bonds, and then we also have ring strain. So one thing about conjugating double bonds is that it decreases the frequency, right? Decreases frequency. Think of the frequency as how stable it would be. If something is conjugated and a conjugated double bond, it's going to be a lot more stable than something that would be unconjugated, right? And the same thing applies to then it's going to be at a higher frequency, right? It's going to shake more violently. So whenever we look at this, we have this compound which has a conjugated double bond, right? So double bond. This one which just has a double bond. This one it just has a double bond and the ketone. And the last one, which has no double bonds except for the ketone double bond, right? But it does have ring strain. A 4-carbon molecule has a lot of ring strain. So ring strain increases, right? So because of that, because we have one with ring strain, this is going to be our highest frequency. So it's going to be our number 3. And now our lowest frequency is going to be our conjugated double bond. So R1, and then this is going to be our second one, right? So are there any questions about that? How we got to that answer? No? No questions? Okay. So Calicene has an unusually large dipole moment. Explain why. So this is kind of, I don't know if you guys will see anything like this on your exam. I feel like this kind of question will be replaced with the Diels-Alder question. I'm still gonna go over it though. So this is Calicene. So it's saying that it has an unusually large dipole moment, and it wants to know why, right? So the first thing we should do is include a relevant structure, right? So it's not very obvious, but what you need to do for the relevant structure is to move the double bond off to this. So this carbon is already sp2 hybridized. All the carbons in this entire thing are sp2, right? So this is sp2, 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 sp2. All of them are sp2, right? So what we can do here is we can use aromaticity to explain it, right? So if we were to draw this arrow and then show that we have we have this plus charge. So if you look at each of these rings, there are 2 rings that are connected by one single bond, right? All of them, let's just assume they're all planar. All of them are sp2, right? So now, whenever we look at this left ring, we have 1, 2, 3, 4, 5, 6 valence electrons, or pi electrons, right? So 6 pi electrons. And on the left side, we only have 2 pi electrons. So both of them exhibit aromaticity. So both of them are aromatic. They're 2 aromatic rings. And so what that means is that they're going to be very stable in the way that um they're going to be very stable, which is going to cause them to have a large dipole moment. It's a little bit weird to explain, but essentially all you have to write for this kind of question is just both rings are aromatic, contributing to their stability, right? And increasing their dipole moment. I don't know if she's gone over this Calicene directly in class. Has she? Then I highly doubt it's gonna be on your exam. This is probably just gonna be replaced with the Diels-Alder question. But it's still nice to know. If you see something like this, it's likely to do with aromaticity. All right. So just put something about aromaticity, see what you can, and then you should be okay. All right. Any questions on that? Nope. All right. So on to our first reaction question. So we have 2 benzenes. One of them is going to be a nitro, and the other one is a anisole. right? We have our anisole and the nitrobenzene. So our first reaction, HNO3, H2SO4. So this adds NO2 to the ring, so it adds a nitro group. And then the second reaction is our Birch reduction reaction. So both of these reactions are new, so we will look into it. So whenever we are looking at which ring to add the NO2 to, we have to look at which ring is activated, right? So this NO2 is a electron withdrawing group, and that is deactivating the ring. Versus this OCH3 ether, this is an electron donating group, and this is activating ring. So electron donating groups, especially this OCH3, they are ortho para directors. So this NO2 is either going to go in a para position or an ortho position, right? One thing to note is that if you put it in the para position, it's going to have a lot of steric hindrance with this huge benzene, right? So it would be easier for it to go onto an ortho position. So if we put the NO2 here, it'll be a lot easier to put it there than to put it on a para position. So our first step is going to cause it to go into the ortho position, right? Then we have our CH3. Then we'll put the NO2 here. So notice how we didn't put the NO2 on the other side because then we would have what 1, 2, 3, right? Groups like on adjacent carbons. It wouldn't be very stable, or the steric hindrance would be pretty high. Versus this one, we have a completely open side. That's why we put the NO2 on this ortho position, right? And so now what does a Birch reduction do, right? So the Birch reduction, it takes away one of the double bonds of the benzene and it causes it to have two double bonds in the ring instead of three, right? But these double bonds will never be touching an electron withdrawing group, okay? So whenever we're drawing these double bonds, let me just draw the rings real quick. Our OCH3 and O2. So we have both of our NO2s are going to be electron withdrawing groups. So if we put the Birch reduction over here, it wouldn't work, right? So we would put it the next best place right here and right here. So what that's going to do is that's going to keep it away from any of the withdrawing groups, and it's going to be stable in that way. And then on the right one, we're not going to put it like this because it's going to be touching the NO2. But if we put it like this, that way it wouldn't be connected to the carbon the donating group would be, or the withdrawing group would be, it would be completely stable. So that's going to be where our double bonds would be in after the Birch reduction. Any questions on that? No? Okay. So now we have Friedel-Crafts, right? So the first step is Friedel-Crafts, so FC. So what Friedel-Crafts does, it essentially just adds it adds in a ketone, adds ketone, right, or an aldehyde. In this case, because we have CH3, CH2, it's going to be a ketone. So our first step, we're going to look at this group. This group is an electron donating group, right? And so that means it's going to be an ortho or para director. So if we put the ketone onto this side right here, it would have quite a bit of steric hindrance, right? So we're not going to put it there. Instead, we're going to put it at the para position. That way, it's as far away from the electron donating group as possible, right? So put it all together. and then this. Okay. And then next, this ZnHG/HCl. What this is gonna do, this is gonna reduce our carboxyl groups to alkanes. So this double bond O is gonna no longer exist, and instead it's just gonna be a 1, 2, 3 carbon alkane, right? So that's gonna be number 2. 1, 2, 3. So that's a 3 carbon chain, right? And lastly, we have Br2 FeBr3. So this is going to be adding a Br. So we have two options, right? We can go with this electron donating group as the director, or to this electron donating group as director. But the SCH2CH3 actually has lone pairs on it, right? So this is going to be an electron donating group by resonance versus the bottom one is going to be by induction. Because of that, the electron donating group by resonance is going to be much stronger, and so it's going to be our director. So because it's our director and it's saying orthopara, the para position is already taken. So we're going to put a bromine on the ortho position, and you can put it on any ortho position. Right. So then our final product will look like this. Um, 2, 3. Then we have our bromine. Right. Any questions on how I got that answer? No questions? Okay. Next one. So we have sodium dichromate, H2SO4 at 100 degrees Celsius. So what this is going to do, this is going to cause all alkanes connected to the benzene ring to become carboxylic acids, right? So this is going to oxidize alkanes to carb acids. This CH2Li is going to, it's kind of like a Fischer esterification. So it's like, except it's going to take the place of OH in the carboxylic acid. So it takes OH place in acid. And then CH3, we have aniline, I think, for sure. And that's going to be kind of like our Grignard reaction. It's going to attack the partially positive carbon and protonate, right? So the first step for number 3 is gonna oxidize our alkanes into carboxylic acids where it can, right? So this T-butyl group, there's no way it can become a carboxylic acid, right? So we're not gonna oxidize it at all. Instead, this alkane group is going to become our carboxylic acid, right? So O, then we have our carboxylic acid, then we have our T-butyl group. And so now next step. So even though it says two equivalents, it's only ever going to attach one group onto it. So this CH2Li attached to the benzene ring is going to be what's attached to this OH instead. So what we're going to have is our benzene group O that, then our double bond O this, and then this is going to be our CH2. This is going to be attached to the big benzene ring. And then we have our T-butyl. And lastly, that our third step is going to attach the partially positive carbon and then protonate the oxygen. So it's going to attack like this. So we've all seen this mechanism. It looks just like Grignard. Then the O minus is going to go and attack this H3O plus and become OH. So final product. And we have our OH, CH2 dash our benzene, and then this is our TBO group. Any questions on that? I got that answer. Anyone lost? Yeah. So the triple bond doesn't attack. It's the minus charge on this carbon that attacks the lone pair. Yeah. So this carbon has a lone pair on it, and so that's going to be what attacks that partially positive carbon. Oh, sorry, I completely forgot to draw it. My bad. Yeah, that's on me. C triple bond C dash CH3. That is the correct answer. Any questions? Okay. Yeah, my bad about that. Okay, next question. Our first step, Br2 light. This is the first reaction we've learned, so that's nice. So our first step, we're gonna put the Br2 on an allylic position. So this is an allylic position. I don't know why it's not NBS, but I guess it's not NBS because there can be resonance, and then you can put the bromine right here. So technically, this Br2 light is it's not the best, but I guess it makes do. So we have our Br, right? This is going to be para to it, so we're gonna do it like this. Br is attached right here. And now we have our NaCN DMSO. So this is an SN2 reaction. So very Ochem 1-esque. And then this is a Grignard reaction. So whenever we have the SN2 reaction, we're just going to take the place of the bromine, right? So our second step is going to be this bromine. And this is going to be CN, cyanide. So this CN is actually C triple bond N, right? So that's going to make this carbon very partially positive, which is going to make the Grignard want to attack it. Let me, okay, yeah. And so whenever the Grignard attacks this carbon, because it's a cyanide, this actually doesn't go all the way to like an alcohol. This stops at the ketone, okay? So even though it has the then H3O plus, it's not going to go all the way to the alcohol. It's going to stop at a ketone. So that's just one nuance with the cyanide, right? So 3 Br, then we have the same C. So this is the same carbon. This is going to be now attached to an oxygen, and it's going to have this group attached to it. So CH2, CH3, and then this was like that. So that will be our final answer. Any questions on that? No questions? Okay. How's the time? 48. Oh, okay. We're going a little fast. My bad. Okay. So I think this is on a lot of your exams. So first thing you want to do with this, I forgot what it's called. Dithiol? Dithiol? Diethane? Diethane. Okay, so this is diethane. Okay, good to know. Right? And so what we want to do for this reaction, it's a lot easier than it looks, right? So we have this aldehyde on the right side. The first step that you guys can do is just draw like the squiggly line right where the aldehyde connects to the main carbon chain, right? So what this does is that it gives us our second step, right? So our first step right here is always going to be BULI. Okay, so what this does, this has two hydrogens attached to it, right? So what it causes it to do, the first step, is that the diethiene is going to have a hydrogen, but it's also going to have a lone pair now, right? And so then this lone pair is going to be wanting to attack something, right? So let's give it something to attack. So second step, remember we drew this line right here. So essentially what this is saying is that this entire group on the right side of the line is going to be our um second step. Okay. So we'll do that. We'll draw it real quick. So just draw it the same way. Right. And then at the very end where this line should be, um it would be a BR. We'll put a BR here instead. So what this is gonna do, this minus charge is gonna attack this carbon right here, right? And that's gonna kick off the BR and is gonna put the dithione on top of that, onto that area. So this way we'll have something like this. Right, and this is gonna be bonded to this. And then so now that we have this, all that's left to do is on number 3, we can put our H3O plus and HgCl2, and that's going to cause it to become a carbonyl. Okay. So there are two ways you can have this problem. You can also have it as a ketone. So instead, let's assume this was CH3, right? All you're gonna do is that you're gonna make this bromine into a secondary bromine, right? So this bromine would change to, let me do this in a different color. So if I did this in, let's choose purple. So if I did CH3, right? Then this second step would now look like this, right? So we'd have our bromine right here. That, that. So it'd be the same thing. It's just that the bromine would now be on a secondary position. So whenever we drew this second steps product, it would look like this instead, right? S, S, right? Instead of having just the hydrogen there, right? It would have a methyl group, CH3. And so whenever we protonated it with HgCl2, it's going to become a ketone instead, right? So because we have an aldehyde here, we're not going to do that. But if you guys did have a ketone, that's how you would do that problem. Any questions on that? This is kind of like just a memorization thing, I guess. So, yeah. Okay. So, final reactions question. SOCl2. So, what this does to a carboxylic acid is that it causes the carboxylic acid to become an acyl halide, right? So, our first step is going to cause this carboxylic acid to become a Cl right there, right? And then we're going to see the same thing. This benzyl group C times 2, CuLi. And remember, this doesn't just add 2. It's just because it has 2 of them doesn't mean it's going to add 2. So this is only going to add 1 onto the chlorine area. So our second step is going to be our ketone plus our CH2 benzene group, right? And now we have fuming H2SO4, right? So fuming H2SO4 adds HSO3 or SO3H, I guess. Better way to put it. And so now what we have is we have 2 rings that can be be a potential candidate for where the fuming H2SO4 goes, right? We have this ring on the right, which is going to have which is now going to be deactivated. It's going to be an activated ring. This is because it has the CH2 group attached to it, whereas this ring on the left is a deactivated ring because it has our ketone attached to it. and this ketone is going to be an electron withdrawing group, and this CH2 is going to be an electron donating group. So it will be attacking on the right ring. So this SO3H will be attacking where the CH2 is the director, and CH2 is an ortho para director. So if we put it ortho, maybe there's gonna be some steric hindrance, so it's just easier to put it on para. So we'll put the SO3H on a para position, and so our final product is going to look like this. H2, yeah, okay. Then we'll put it on a para position, SO3H, right? Any questions on how I got that answer? No questions? Okay. So next step, our next problem is the mechanism problem. So this mechanism problem looks pretty difficult. Like, it's very hard to visualize how this thing is gonna come and create all of this. So the easiest thing to do is just to start, right? So we have an HF, right? And so we can have these lone pairs attack it, and that's not going to do anything because that's going to be a vinyl OH, right? It's not really very reactive. Versus this OH, which is now vinyl, it can definitely take one of those hydrogens and become H2O, right? Let's try that. One thing about mechanism is that it's just hard to get started, but once you get started, it seems like all the pieces fall into place, right? So that's one thing that we can do. H. So this oxygen now has a positive charge. It's H2O. One thing we know about H2O is that it's a good leaving group, right? And so what does a good leaving group do? It leaves, right? So we can show this bond breaking. And now our second, we have CH3, the benzene. That is not para. This is para, right? Yeah. Okay. And then, so now we have a plus charge right here. Okay. So now, let's look at this. This OHCH3, this is going to be this OHCH3, right? So we're not going to worry about this side of the problem. We'll worry about the left side. So we have this CH3, and because this OHCH3, this is attached right here, okay? So we'll cut off everything from right here, and we'll only focus on um all of this stuff, right? Focus on this and this methyl group right here, okay? So whenever we look at this CH3, it has 1, 2, 3, 4, 5 carbons, right? And on carbons 3 and carbon 4, it has a methyl group. So CH3, both carbon 3 and carbon 4 have a methyl group. Now, if we look at it this way, 1, 2, 3, 4, right? So this is a 4 carbon chain instead. So it's a little bit oh wait, sorry. I didn't take into account that this was a full CH3. So this CH3 right here on carbon 3 is actually the CH3 that is attached to this OH. Right? So we won't worry about that. I lied. Again. I confused myself. Okay. So we are worrying about that. Don't. So we have the CH3 right here. Okay. On carbon 3, we have a CH3. And on carbon 4, we have another CH3. And then we have a 5 carbon chain. Right? So did I?
Yeah.
I did. Okay, you're right. So it'd be a 4 carbon chain. Okay. I started counting from the same. Hold on. 1, 2, 3, 4. That makes it a lot easier. Okay. So 1, 2, 3, 4. And so now on carbon 2 we have a methyl group, and on carbon 3 we have a methyl group. But whenever we look at this one, our carbon-2 has 2 methyl groups and our carbon-3 has no methyl groups except for the 4, right? So what we can do is we can have a methyl shift. So this methyl is going to go and stabilize this positive charge, and so the positive charge is going to go onto carbon-2. So now, whenever we do that, we have this CH3. Now our plus charge is on carbon-2, right? So this is exactly what we needed. If I count them, 1, 2, 3, 4. So carbon-3 has a methyl group, carbon-2 has a methyl group. All that is perfect, right? And so now finally what we can do is that we can make one of these double bonds attack this positive charge so that it can create a bond with it, right? Because the bond attached to this OH is attacking this is attacking that group, carbon-2, right? So if we draw that like this, we can do this instead, plus OH and CH3. I'll actually draw the bonds actually. So it goes like this. And so let's say this bond attacks this. It's ortho to the OH. So now whenever we draw this, we can. I'm gonna draw it in a different color. So CH3. Okay. Okay. And now whenever we draw that, we can draw I'm gonna put the methyl group facing up. So just so you guys know. So this pointing down is gonna be where it bonds to, and it'll bond to this carbon right here, right? So that will be that carbon, and then we'll start putting our benzene ring. And so now this is gonna be where our OH, yeah, it's OH. So that's gonna be OH. This is going to become a CH3. And because this double bond was broken, right, we're only going to have double bonds here and double bonds here. And that's going to cause, because this bond used to have 4 bonds to it, now it only has 3, this is going to have a plus charge onto it. Okay? So that was just one step. Okay? So what I did here, I just attached them together by the way that it was shown in the final product. All right? It looks a little bit different, but I can assure you it's the exact same connection. Okay, so next. Now, one thing that you guys have to do in this exam, when more than one resonance contributor may be drawn, be sure to draw the most stable contributor. So technically in this one, you only have to draw one resonance contributor to show the most stable, but I think it's in good practice to draw all of them just so that you can get all the points, right? So we have one resonance contributor that this lone pair attacks and creates a double bond OH with the OH having a plus charge. We also have this double bond attacking to create like a Birch reduction kind of product. Then like to follow that, we can also do something like this, which just moves the double bond. So we have to draw 3 extra compounds just to find the most stable resonance contributor. This is a very important part of your exam. I think this is worth about like 4 points, 2 or 4 points, something like that. So try not to forget about it. So I'll draw the OH group resonance contributor first. Um, oh, that's weird. Come on, wait. Okay, then we have this. So that's one of our resonance contributors. From this one, we don't have any more, right? So, but if we went down this way instead, we drew this resonance contributor, we can do like this. Right. So that's another resonance contributor, and we have one more where this double bond can come and take this. You'll have to draw that methyl group. Okay. So that will be like this. Alright, so that's going to be our third resonance contributor, and this is going to be where our plus charge is. So, kind of running out of space, but it should be fine. So, you don't have to identify which one is the most stable, but if you guys do want to know, this one is going to be our most stable resonance contributor, even though the oxygen has a plus charge on it. It's because every molecule has an octet. So this OH is going to be this part is going to be our most stable. Either way, that doesn't mean we're going to be using the OH to be our like guinea pig for the final step. So our final step, remember we took off this H from this F, so now we're left with F minus, right? So this F minus can act as a nucleophile and do something very similar to like a E2 reaction, right? So if we just did this one, I guess we have a hydrogen right here, right? So what this F minus can do is it can go and attack this hydrogen and it can create this double bond right here, right? So this is kind of like an E1 reaction actually, not an E2 because it doesn't have any halide there. So it's kind of like an E1 reaction. Essentially, it creates the double bond right there. And if you notice, that is exactly the molecule that we have up here. So our final step was just to create that double bond. And now we can draw an arrow back to the final product. Any questions on that mechanism? I know it might have been a lot. So yeah. Yeah, no, it shouldn't matter which one you pick for the resonance thing or for the F minus. For this one, I wouldn't use this one or this one actually, because there's no way for the F minus to attack that oxygen, right? The F minus wouldn't attack the oxygen. And if it attacked over here, then you would be a little bit of a pain, just like because neither of these adjacent carbons have hydrogens attached to them. But for example, if you use this one instead, this carbon has a hydrogen attached to it, and you can just show it going like that. No, that's completely fine. I just use this one for, out of convenience. Yeah. Any other questions? All right. So on to synthesis. So the synthesis is, I feel is pretty interesting. Right. So in this one, we have two benzene rings connected to an ether. So the first thing that I tend to do is just get rid of the ether because it becomes very annoying to deal with. So our first step will have our NO2 bonded to the benzene ring, and then this is meta to this CH2, and then we'll put a Br right here, plus our O minus, right, and then NO2 is para. So notice this is just a regular like SN2 reaction, right? The O minus and A plus, it goes and attacks this carbon and just creates a bond, right? So it's just a very simple SN2 reaction to start off. So I'll start on the left side because the right side is a little bit easier. So on the left side, the first thing we can do, we notice, is that we have a BR on the very end, right? So if we use BR2, 2 slash HV, this would actually put the BR right over here because it's in an allylic position. And the same thing would go for, um, the same thing would go for, what's it? I'm completely blanking on the name. Same thing would go for NBS and light, right? It would still put it right here. Or it would do some resonance. So don't use BR2 light. One thing I would use instead is HBr slash peroxide. So what this does, this is an anti-mark reaction with alkenes, right? So it'll put the Br on an anti-mark position. So NO2. So what we'll have here instead is a single bond and then a double bond attached here, right? So now we have an alkene. And these are meta to each other. Did I draw them para? I think I did draw them para. Yeah, I did. Okay, let me redraw this real quick. Right, because they're meta here, so we're gonna keep them meta. And now, uh, what we can do is we can take out this double bond by using acid dehydration. So H2SO4 slash heat, and that's going to give us our OH. So we have like this, our nitro group 2, and then our alcohol H right here, like that. And so now next step we can do is actually Grignard, right? So just right here, we can do this. This is NO2, and right here we have MgBr plus our, this is going to be an aldehyde, right? And so we'll just use PCC to get into an alcohol. So OH, and this OH, alcohols of 2 carbons or less. Perfect, exactly what we needed, right? And this is going to be meta, not so MgBr. Now we can use Mg slash ether and O2. Oh wait, actually we cannot do that. I lied because the NO2 is a deactivator for the ring. So whenever we do FBr2, FeBr3, it's not actually going to be a reaction. So we have to do a different way, I think. So instead of this, sorry about that. We can use instead we can use LiAlH4 OH4 slash H3O plus. And so what this will do is that this will cause a ketone to instead become a alcohol, right? So we have an alcohol here, so we'll start with a ketone, 2, meta position. So now it is a ketone. And so now we have 2 deactivators on the ring. And so what we can do here is we can just take off the HNO3, right? So HNO3 slash H2SO4. So now we have just our ketone on the ring. Yeah, that was it. We just have our ketone on the ring, and now we can use fetal crafts. So AlCl3, and our ring now has ring is now free. And we have our ketone with the Cl on one side, right? So all that together, we can use SOCl2. This is going to cause it to become a carboxylic acid, OH, and we can use Jones reagent, Jones, to create a primary alcohol right there. So that was the left side. So in this case, you wouldn't be able to use Grignard because if you use Grignard, then it would cause it to be it would be the bromine and the NO2, and the you wouldn't be able to attach the bromine because the bromine would be on a meta position, right? So essentially what was happening is that we were creating this. So NO2 and bromine on a meta, right? But NO2 is a deactivator, and so it would have to be our director. But this bromine would actually be our director, like in if we actually did the experiment, right? So this FeBr3 would not actually occur in this way, right? So we had to take off the NO2 first so that we could continue with the rest of the reaction. So next one on the right. So we have O minus Na plus. So the first thing we can get rid of that is just using NaOH, two equivalents, right? And that's going to cause it to just become a Br, right? So we have Br, and then we have our NO2. Can we do that? I think we are able to actually. Might have lied. So maybe there are two ways to do the left side because this is the only way to do this is to do this NaOH two equivalents and then have the NH and oh yeah, sorry. We have to take off the HNO3. On this side, it would cause it to become ortho or para, right? But on this side, because it's para already, it can't be meta, or it's not meta. So we are able to do this reaction. NO3 H2SO4. Finally, we have our bromine, and we can do Br2 slash FeBr3. And that will give us our product like this, right? So I might have confused some of you guys. If you guys have any questions on that, please say something. I know I kind of went back on myself a couple times. Any questions? None? Does that make sense why I can't do Grignard on the left side? So
Explain that again.
yeah, perfect. Okay. So on the right side, we have Br and NO2. That's going to be para to each other, right? And so that means that the Br is our director, which is correct. We want the Br to be our director. But if we did Grignard here, have meta position, or so we have NO2, this, then we have Br, right? But this time Br would still be our it would still be our, what do you say? It'll still be our director, right? And Br is an ortho para director. So whenever we take off this NO2, we can say that the HNO3 slash H2SO4, this NO2 would not go into the meta position, right? The NO2 would only ever go into the meta or the ortho or the para position, never the meta position, because the Br is the um is the director, right? Versus on the right side, since the Br was the director and it was para, it's completely fine. But on the left side, because the nitrogen, the nitro group that we want to take off is on a meta position, it's not going to ever go to the meta position because the Br is the director. That makes sense? Hope that summed it up. Okay. Any other questions? All right. Final section. We have spectroscopy. Very fun. Okay. So the first thing for spectroscopy, we want to look at the whatever this is called, the elements. So remember the formula is 2C plus 2 plus nitrogen minus hydrogen all divided by 2, right? So if we put it in 22 plus 2 minus 14 all divided by 2 comes out to be 5. right? So 24 minus 14 is 10 divided by 2 is 5. So whenever we have a number greater than 4, it means we have a benzene ring, right? And any number more than 4, right? So we have 5, right? That means that we have one double bond. So we have a benzene ring and one double bond attached to it, okay? So we'll work with that. I want to skip over the spectroscopy and go straight to the proton NMR. So we see this doublet peak from 7 to 8. Or yeah, we see the doublet peak 7 to 8. That tells us that this is benzene peaks, right? Peaks. And remember the doublet peak tells us that it is okay. So we already have some nice clues to where we are. Okay, so we'll start on the right side. So 3H. So we have a CH3 that is bonded to something that has no carbons attached to it. It's at the very end, and it's attached to something um that is slightly downfield, right? Because normally this 3H peak, if it was attached to nothing, that was it would if it was attached to nothing deshielding, it would probably be around sorry, it would probably be around like between 0.5 and 1, right? But because it's even past 2, whatever it's connected to, this thing is lightly bonded to something that is deshielding, right? So it's probably bonded to an oxygen. Okay, so we have that. Now we have 2H triplets. Okay, so this 2H triplets tells me that we have CH2 bonded to CH2, and there's nothing more than that. It's only these two CH2s. If they had a third CH2 like this, then this would have um bonding on either side, right? And so it would become 2 plus 1 times 2 plus 1, which would have a 9 peak. And because we don't have that 9 peak, we could say that this is only just two CH2s bonded to each other, right? And both of these are slightly deshielded as well. So perhaps they're bonded to something that is uh deshielding, right? And then lastly, we have this 3H that's highly deshielded, right? So CH3 bonded to, and the only thing that would be deshielding like that would be like an ether. So this is 100% CH3 bonded to an O. Okay. So now if we put all the pieces together, what we can have is that we have found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons and 11 carbons. Right? And so that's exactly the number of carbons that we have. One thing I like to look at sometimes is this carbon 13 NMR, and I see that this peak is all the way past 200. So if you go to your formula sheet and you look over here, past 200, we have aldehydes and ketones, right? 182 to 215. Even carboxylic acids and esters. What happened there? Even carboxylic acids and esters, 160 to 185. And we don't have any peak from that range, right? So there are no peaks here. So it's likely an aldehyde or ketone, but we do have a group right here that is attached, a CH3 that is attached to a carbon that has no hydrogens on it. If it had a hydrogen on it, then this 3H would likely be a doublet, right? So that means that we have a ketone. So this would be our ketone right here. So we have our double bond C. And then one thing we can put is a CH2, CH2, which makes sense because these are slightly deshielded as well, which would make sense if they were near a carboxyl group, right? So we've made one of our substituents. And so that accounts for 4 carbons out of our, that accounts for 10 carbons already, right? We have the 6 on the benzene ring, then we have 4 right here. So we have 1 carbon left, and we have an OCH3, right? So we found one of our substituents as being this, and we found our second substituent being our OCH3. So if we put it all together, we have a benzene group that has CH2, CH2, double bond, oxygen, bond to a CH3, and then para to it, we have an O-CH3, right? And this makes sense because we have both oxygens. We have an extra double bond, right? We have an extra double bond right here. We have our OCH3 group. This shows how this is deshielded. We have two CH2s that are slightly deshielded, and that if you look at this side, no, there's no hydrogens here, so it wouldn't have any anything there. So it all of it has come together, and we have made our final products. Any questions on this question, on the spectroscopy? Any like things that you guys might want to say? And I guess that's it for the exam review. Yeah, you have a question? What time I can't? Am I missing a CH2? Well, oh, I am missing a CH2. That is correct. So just like that, beautiful. And so now we have our two CH2 group. Thank you for pointing that out. Appreciate it. Any other questions? Okay, well, that's gonna be it for our exam review. Good luck on your test Friday. Hope you guys do well. Yeah.
Thank you.
Yep, no problem.